Hi, how's everything going? Yeah. So any PA5 or lab issues? Zenity issues? All good?
I've been trying to run Zenity on Ubuntu. And
Okay.
also on Sigma, and every time I try to run it, like it's a network error or something. It's trying to connect to something, and I don't know why.
So you're trying to run it on Ubuntu on your own machine?
Yeah.
It should work pretty direct. Is this a Linux system or is it Ubuntu under Windows?
I think it's Linux. I don't remember, but I tried the same thing at 6, which should be Linux.
So Windows 10 comes with a version of Ubuntu that you can run, and Zenity does not seem to work well in that. Okay, it wants to create an X Windows connection, and it gets complicated. Sigwin should work, but you have to set it up just right. And I've had several people come by, and we've been able to get it set up. But the two main things you got to do, the biggest thing you got to do is this. Okay, you've got to have this export. And you either have to type that every time you log in or put it in your bash RC file so it automatically executes. But from the command line, you can try typing this in and then run your Zenity command and see if it works. So there's two things. First, if you say /bin/Zenity/bin/Zenity, it should give you a Zenity error message. If it gives you an error from bash saying command not found, then Zenity's not where it should be. Okay. If it says you need to specify a dialog type, or it gives you a big long error message about some library that's missing, then it's running Zenity, but it's probably missing this second line, this highlighted line, which basically tells it where to find the files that it needs.
All right.
And if you put that, if you just vi ~/.bashrc, and you put it at the bottom of that file, this file gets executed every time you log in, so it'll set up that export for you. This first line, which is the alias, helps from the command line, but it doesn't really help from inside scripts, because the scripts don't seem to pick up the alias. So in your script, every time you want to run Zenity, you got to kind of type it in /bin/Zenity/bin/Zenity. Or get fancy and make a link to it somewhere or something like that. But worst case, you can just use the full path. If neither of those are getting you there right, definitely let me know as soon as possible. Do you have your laptop with you today?
I don't have a laptop.
Oh, it's a desktop? Okay. Yeah, give it a try and let me know. All right, other questions, issues? Yeah.
Is there a way to turn on syntax on Sigma?
Syntax highlighting?
So that it identifies what's a variable or.
Oh, probably, but I don't know how. That's a good Google topic. Yeah. I don't know how to do that, but it's a dot something file that you put in your home directory probably.
Okay.
And sometimes you can hop onto the Linux server and do an ls-a from your home directory, and one of these will probably be the file that you need. And sometimes you can just copy and paste it if you get lucky. But that and Googling should get you there. If not, let me know. I'll help you Google. All right, I'm going to try to post a list of topics for the final sometime in the next day or two, just to have it up there. Yeah.
For VE5, for the bags, how many bags we have to be? It has to be a number between like 0 and 3, you saying?
It's up to you.
Oh, okay. Then if we have the number between 0 and 3, or like 5, or whatever the number, we have to strict like to not use a word like 0.1, let's say 0.5 or something. Or we don't have.
It's up to you. If your user is really, really kind of bent on trying to crash your system, right, that's a really hard problem. And I'm going to let you demo your program, right, to the class and to me, and show me how it gets used. So you kind of get to drive it how you like. I may ask you to do a few things, right? Like if every time that you demo it, they're leaving from the same place and going to the same place, I might say, you know, can you leave from a different city and show us how that works? But, you know, within reason, I'm not too worried about it. So if you want to assume that they're going to type in a real number, you know, 2, 3, 5, something like that, that's fine. You don't necessarily have to catch
And let's say
silly.
if they go 1.5, let's say we round it up, or we
It's up to you.
make it down.
You can say you obviously aren't old enough to travel, goodbye, and just kick them out if you like. Totally up to you. Yeah, same thing with maximum number, right? If you charge $100 per bag, you might not want a maximum. If someone wants to bring 50 bags, it's $5,000. But it's your choice, your design. So this is where you can be creative, right? So I'm deliberately putting very few rigid requirements on this. So spin it as you like. So presentations will start on Friday. Assuming you're doing this on a laptop or a tablet, right, or something that you can bring up. So I have HDMI, a full-size HDMI connector, and I have a VGA connector. If you need some other kind of connector, you probably want to either provide that or talk to somebody who might have one. I have one weird dongle that works with some tablets, and I'll try to bring that in. And I have one that works with like Samsung's, and I'll try to bring that in. And I have a wireless adapter that sometimes works under Windows. So we've got some flexibility, but think about how you're going to actually display. And worst case, you know, you can take the camera and point it at your screen, and we can go, you know, hey. So there's options. All right, so let me talk a little about low-level IO, because this will come into what we're going to do tomorrow. So, I told the other class this also. I'm not going to hold you responsible for details of what we're talking about this week as far as processes and forks and all that kind of stuff, right? I want you to see this stuff because more and more we're working in some sort of embedded environment where we're either on an operating system with other processes or we're interacting with a cloud or something, right? We're not just kind of sitting in a little box reading variables and adding them together and printing them out. A lot of times what we're doing is working with other processes. So I just want you to have some exposure in this class to the idea of processes, how they get created, and so on and so forth. In 223 in spring, we'll do multi-threaded programming, where we'll deliberately have more than one process running simultaneously, and we'll see some use of that. So we'll revisit some of these, but that'll be in Java, and this works a lot more cleanly in Java than it does in C. But C kind of gets you down to the low-level version of how this stuff works. So I just want you to have seen it, but I'm not going to, you know, ask you to write code that uses forks and all this kind of stuff. So you can kind of relax and take in what we're going over and ask questions if they come up, but it's more just for your information. So we know how to read and write from files, right? We can use fopen to open a file, and that gives us back a file pointer. And then we can do fgets with this file pointer, or we can say fprintf with this file pointer. And so we can read stuff in from a text file, we can write stuff out to a text file, and so on. This is kind of an expensive set of operations. When you do an fprintf, right, you can put in a %d and you can take this integer and you can change it into a bunch of ASCII codes that correspond to the integer value. Or %f turns it into a floating point number or scientific notation or something like that. When you do fgets, you say, I want to read into this string that holds 120 characters. But if you hit a new line, right, stop reading and fill in the string, null terminated, and come back from fgets. Right, so new lines are special characters. When we fprintf or when we fgets, we don't really want to read \0, right, because that's going to terminate our string. So these are kind of high-level routines. They're good for sort of human-level interaction. But they're not really good for computers trying to read and write low-level things, particularly if those low-level things are other computers. So if you're trying to do networked communication to another machine, you don't really want to do things like fgets and fprintf, right? So these are sort of high-level routines. And if you look at the manual pages, right, if you do a man on fgets or fgetc, that little 3 on the top in parentheses, that says this is chapter 3. Okay, chapter 3 is sort of the user-level code. Functions that you would generally call from a C program as a user. There's another set of functions in chapter 2 which are lower level. These are sort of system level functions, things that you wouldn't typically call if you were just writing a C program to, you know, compute mortgage or something like that. These are lower level. These are the system versions. And the main things that we're going to work with there are open, read, write, and close. And there's also an fclose over here. Right, so these are chapter 3, system level. These are user level. These are chapter 2, system level. And these are very close to the metal. Okay, these are pretty unadorned. If you read from something and you happen to read a null terminator, it just says I read a null terminator. If you happen to read a new line, it says I read a new line. If you write a null terminator, it writes a 0, right? There's no special handling going on in these routines. And these higher level routines are really just wrappers around these low level routines. So fgets ultimately does a bunch of reads, but as it reads character by character, it says, is this an end of line character? Is it a new line? And if it is, then it stops reading and it puts your string together and so on. But read doesn't really care what it's reading. So open is used to open a file, and it gives you back an integer, right? Fopen returns a pointer to this structure called a file. Open just gives you a plain old int. And the arguments to open are the file, right, or a path to whatever it is you're trying to open, and then an integer that says, do you want to open this for reading, for writing, for appending, right? So that's what the flags are. And read basically takes a file descriptor, which you get from a call to open, a pointer to a character, and how many things you want to read. And we'll try to read that many bytes on the file descriptor and store them at whatever your buffer is. And write just goes in the opposite direction. You give it the file descriptor, pointer to characters, and say how many characters do you want to write, and it takes that many characters from your character array and it forces them out through that file descriptor. All right, so let's open a file called haha. We're going to open it for writing. And we're going to take whatever that call to open returns. We're going to store that in FD, which is short for file descriptor. We'll print out the value of FD, and then we'll close our file. And where does open come from? Do I really need all of that? Good enough. Oh, and this is bogus. So these flags, so they can be O underscore read only, O underscore write only, or O underscore read write. So I'm going to open this for writing. Rid of that. So I have no haha. Let's go ahead and run reader. And oh, return from open equals -1. Okay, we encountered an error for some reason. So it doesn't create files by default. When you open them for writing, if the file doesn't exist, you're going to get an error. So we need to modify it with O underscore create. So what's going on here? This is a low-level routine, open, right? Its second argument, which says how do we want to open the file, is just a plain old integer. It's not like quote W or quote W plus or something. It's just an int. And so an integer, right, has 16 or 32 bits associated with it. And each of these bits can have a particular meaning. So we can treat an integer as really a collection of flags. And so these things like O underscore write only, or O underscore create, these are certain bit patterns. WR only. These are certain bit patterns, okay? And so the way we use these in code is we OR them. Right, so we logically OR these together. What happens when you OR two bit masks together? Right, this mask has a 1 in this position, this other mask has a 1 in this position. If you OR them, you get something which has a 1 in both of those positions, right? So all of these level 2, most of these level 2 routines, if they take masks like this, typically you see a bunch of keywords being ORed together. And let's just look at those. Let's do this first. Let's just look at these magic fields, O read only, O write only, and O create. And let's just see what those are equal to. Right, so read only is 0, write only is 1, create is 64. So if I say I'm opening this file for write only and for creating, it will take 64 and it'll OR it with a 1. Right, that's 64. That's 1. That's what you get when you OR them. So if I pass the number 65 as an argument to open, I'm opening a file for writing, and I'm asking it to be created if it doesn't exist. But we don't put magic numbers in, so we use this structure instead. All right, so there's no ha-ha. Run reader. Return from open equals 3. And now we got a file called ha-ha. So this file descriptor that comes back from the call to open is just an integer. It's a small integer. And it's generally going to be 3 the first time you call open, and if you call open again, it's going to be 4 the next time, and so on. So you always have 3 file descriptors already available. You have file descriptor 0, which is basically standard in, file descriptor 1, which is standard out, and file descriptor 2, which is standard error. So standard error is the stream that stuff is sent to that you don't necessarily want redirected to a file. So if you run a command and you redirect the output to a file, but something gets printed to standard error, you'll see it on your display, even though you're redirecting. So error messages, things that you want the person to actually read, go to that. And then starting with file descriptor 3, those come back when you make calls to open. So it called open, got a 3 back. There's haha. Okay, so let's write something into here. What else should we write in here? Give me a number. What number? 25, good choice. All right, so there's some numbers, right? We got a 1, we got a null terminator, we got a 17, we got 4, which would be control D. Technically, we've got 25. Let's throw in one more nod for Windows. Let's do a 26, which is Windows old in the file terminator. And then let's just do a 65. That's a character A. And so let's write and we'll write temp, and I better double check the order of these things. So file descriptor, buffer, and count. FD, buffer, and looks like we've got 7 bytes to write. All right, so we got an array filled with random stuff. We're going to call write. We're going to try to write all 7 bytes into the file. We'll print the return value from write, and then we'll close the file. You're supposed to find my syntax errors for me.
Or underscore create, that creates the file if it doesn't exist.
That says create the file if it doesn't exist, and this says let's write into the file only. All right, go ahead and run that. Oh, it didn't like that.
Is the create supposed to have a D on here?
No, it doesn't for some reason. Let's get rid of it. Whoa. Got created with a really weird permission mask, though. All right. about that. So let's go ahead and run reader. Return from the open equals 3, return from write equals 7. So open returned to 3, that was the file descriptor. Write returned to 7. Write tells you how many bytes got written to the file descriptor. We asked to write 7 bytes, it wrote 7 bytes, that's good. Sometimes that doesn't happen. Sometimes it writes fewer bytes. I don't think it'll ever write more though. Alright, so I don't know why we've got weird permissions on this, but I'll make the permissions normal. So let's take a look at haha. And it's got weird stuff in it. But Control A is the way it represents ASCII code 1. That corresponds to the 1. Control @ is how it writes a null, which is ASCII code 0. Control Q is the 17th letter of the alphabet, so that's our 17. Control D is the 4. Control Y and Control Z are 25, 26. And the letter A is the ASCII code 65. And so it tells us we've got 7 characters, and it says incomplete last line. There's no new line at the end. Right? And if your last line of a file doesn't have a new line, VI will give you this message at the bottom saying incomplete last line, because VI thinks it's editing text. If we use octal dump, we can look at the contents of this file in octal. And there's character 1, there's a null terminator, there's octal 21, that's 17, and so on and so forth. So this is binary I/O. This is low-level operation, right? And we can write anything we want into these files, and the system doesn't care, right? So if you were making an executable file which has all that gibberish inside, you'd be using open and write and close as opposed to fopen and printf and so on. So here's an input side. So we're going to open something called new file. We're going to try to read in 10 bytes, and I'm going to print out each of those bytes in order, just as a 2-character hex number, and then we'll close the file descriptor. And if we run this, this is what it tells us. The open return 3 again. We know open returns 3 the first time. Read return 10. We asked to read 10 bytes, and it read 10 bytes. So that's why read gave us back a 10. And then here's the 10 bytes that it loaded into this character array called buffer. So here's the file that we were opening. It's a GIF file, actually. No, it's not. It's an old executable. And it's got stuff in it, right? But we can octal dump it and look at the contents of this file in hex. Well, there's a 4D. That's the first byte we read. There's a 5A. That's the second byte we read. Here's a 90. That's the third byte we read. But when we printed it out, it actually printed a bunch of Fs followed by 90. So what's up with that? What does a bunch of Fs mean? Could be, but not in this case. Usually that would be correct. So what does this look like in binary? Bunch of ones. Because F is 15, that's 4 ones. And then we've got 90. So the byte in the file is ASCII code 90 hex. But when we printed it, it printed out as if there were a bunch of ones here. Well, here's what's going on. Right, when we printed this first byte, which was 4D, so there's 4D, it actually thought there were a whole bunch of zeros in the front. And you know, when you print numbers, you usually don't print the zeros in front of it. Right, when you want to print the number 7, you don't say 007. Sometimes you do. So these get suppressed. But when there's ones in the front, printf prints those out. So why are there ones in the front of this number and zeros in the front of this number. So this number has a bunch of ones in front of it, this number has a bunch of zeros in front of it. So the $1,000,000 question is why?
Negative number.
Negative numbers, engineering 250, 2's complement. So a 2's complement number, the most significant bit is a 1 if it's negative. It's 0 if it's non-negative. So if it's non-negative and you're trying to extend it out to 32 bits, you're going to extend it with zeros. If it's negative and you're going to extend it out, you're going to extend it with ones. So this is just an artifact of printf. Printf is looking at this, saying, well, you want to print it as an integer, that's 32 bits. I have to pad some stuff on the end. Since this is a 1, this must be a negative number. So it pads 1s, and then when we print it in hex, we get a bunch of f's. But the actual number is just good old 90 hex. So that's 90, that's 90. There's our 0. There's a 3, and so on and so forth. So we're going to use these low-level routines probably tomorrow when we start trying to talk to processes, or maybe next week. So I want you to be aware of those. All right, so let's talk a little more about processes. So we talked about forks yesterday, right? So this was kind of where we left off, right? So we run C6, it says starting the main program, we do our fork, and then we get two messages saying done with the fork, and one of them said the status was 0, and the other said the status was something non-zero. And so what's going on, remember, is here's your main program. It starts executing. At some point, we say fork, and a parallel process is created. And if we say something like R equals fork, for the child process, R will be equal to 0. And for the original process, which we call the parent, R will be the PID, the process ID of the child. So we have parent and the child process. So we can self-identify right, by looking at the return value from fork, we can check to see if it's a 0, and if it is, we know that we're the clone, we're the child process. Otherwise, it's non-zero, we know that we're the parent process. So now we do that, the main program starts, and now each thread reports its identity. And when I run this, it always seems like the parent responds first. That's not always going to happen. It's possible that the child would respond first because these two processes are basically independent of each other now. So the order is not significant. Okay, so we can create a clone of the process that we're running, and each of those processes can identify itself as being either the original or the clone. Why do we care about doing that? What's the benefit of that? Or is there no benefit? It's just a cool thing to do. So suppose you're writing a word processor and you're going to put in an autosave feature. And every minute you're going to take whatever the person has in their document, you're going to write it out to disk to a temporary file. So that if something happens and the machine crashes and they haven't saved it themselves for an hour, you've got a temporary copy that's no more than a minute old. Okay? So every minute, some timer goes off and says, okay, time to make a backup, and you grab everything that's in the memory and you write it out to a file. Well, suppose it takes 5 seconds to write to a file, right? Because it's a big document. The effect would be you're typing in your document, and every minute everything freezes for 5 seconds while it writes, and you hear your disk grinding, and you get really annoyed because it's like, why is it auto-saving, right? So that's a really bad user experience. So what if you, every minute, created a new process, did a fork, checked the return, and if the return was 0, then you read what was in memory and wrote the contents to a temporary file and then exited. And the original process would make a call to fork, and then it would just go back to doing what it's doing, which is waiting for the user to type and echoing and so on and so forth. And the user doesn't have to wait for this write to disk because there's a totally different process taking care of that. Right? So that's kind of a classic multi-threading, multitasking situation. So that's one reason why this might be useful. Another reason will come up in CSE 223 in spring in Java instead of C. I'm probably going to have you make a chat program. So you can run a program on 2 machines, and you can type on one machine, and what you type appears on the screen of the other one, and the person on the other one can type, and it shows up on your screen, right? And the algorithm for doing this is pretty simple. So user 1, read from standard in, send to user 2, and user 2, read from standard in, and send to user 1. Well, if I just run these 2 loops, right, I'm reading from standard in, I'm sending it to this user over here, but I'm not displaying anything, right? I'm typing and I'm sending, but I'm not actually seeing the stuff that user 2 is sending to me. So I also need to do the following. I need to say read from user 2, and then I need to print that to standard out. And user 2 needs to read from user 1 and print that. So the question is, what does our looping look like? Because we want to do these things over and over and over again. But if I loop like this, I've got a problem. So I'm user 1, I type in some stuff, I hit enter, my fget comes back, I send what I typed to user 2, and now I wait for user 2 to send me something. If I want to send something else to user 2, I can't, because I'm sitting down here in my code. I have to wait until user 2 sends me something, I display it, now I come back up and I do my fgets again. And you're forcing the conversation to go ping pong, ping pong, ping pong. And that's not how we want chat programs to work. You want to be able to just spam the person, not give them a chance to talk, right? So we don't want to do this. What we really want is a pair of loops. User 1 wants a loop that's reading from standard in and sending to user 2, and another loop running at the same time that's reading from user 2 and displaying the standard out. That's two processes. And if you don't break this into two processes, it's very hard to make this thing work. And the reason is that most of our ways of reading from standard in, i.e. fgets, is what we call a blocking read. If you call fgets, you never come back from fgets until the person hits enter. Right, that's just the way fgets works. It sits inside that call, and the user types stuff, and eventually they hit enter, and then it will come back from fgets. Even if you say read 10 characters, and they type 1,000 characters, you're not going to come back from fgets until they hit enter. Right? That's just how it's set up. And unless you have a way around that, you've got to break this into two pieces. So that's going to be an application for having multiple processes. Another application for having multiple processes is this is how processes come into existence on an operating system. Right? If you look on the Linux server, there's a couple of hundred processes running. And let me see if I can get lucky. Hey, I got lucky. All right, so my PS command was process ID 41210. Its parent ID was 195. That's my bash shell. My bash shell's parent is ID 41194. So let's see what that process looks like. And process 4194 is something called sshd :nic at pts/1. And that process's parent was 41185. And if we look for process 41185, that's a process that's also sshd, but that process is owned by root. Right? This sshd was owned by Nick, that's me, but its parent was an sshd owned by root, whose parent was 53538. And if we look at process 53538, that's a process owned by root called sshd, and its parent is 1. And if you look at process ID 1, that's a process called a init. So there's a hierarchy of processes. Init is the process that's created when the system boots. It's the first thing that runs. It's running in what's called single user mode. So if you don't have an operating system, if you have something like an Arduino processor, right, or a PIC 18F1220, I said it, it's just running one set of code, right? There's no sort of processes. So init is this initial set of code that's running, but init creates this thing called sshd, and sshd created another sshd, and that created another sshd, and that created a process running bash, and that created a process running ps. All right? And every time those processes are created, it's the result of calling a fork. So init starts off and it makes a bunch of calls to fork to create all the things that are going to become the other processes on the system. And one of those forks starts executing this sshd. And when I make a connection request by saying ssh nic at Linux, that sshd process executes a fork, and the child that's created starts running another version of ssh that talks to me and authenticates my login credentials and so on. So forks are kind of underlying the whole process creation that leads to all of this stuff. All right, everything that's running out there. Okay, so that leaves us at the next piece, which is exec. So exec is a whole bunch of different functions, execl, execl P, execl E, and so on and so forth. And I'm going to pick on execl. But they all do basically the same thing. Exec basically replaces the current process with something else. You say exec and you give it the name of a file, and it will open up the file, and it should be an executable program, something that's been compiled. And it will find in that program the ones and zeros corresponding to the assembly language instructions for that program. And then it will replace its own memory with those ones and zeros. So what happens if you take somebody else's memories and completely replace your own with them? You basically become the other person. Right? So there's a philosophical issue there, and it's a Blade Runner theme. But this is what exec does. It says, go into this file. Yeah, I know I'm a C program, and I just did a fork, and I've got an if statement and all this, but open up this file called date and find the ones and zeros that correspond to that program, and now overwrite all of my memory with those ones and zeros. And the next instruction that this program executes is not the instruction from the original program. It's an instruction from this program called date. And the next instruction is the next instruction from date, and so on and so forth. And guess what? It's executing the program date. It's changed identity. And so this is how processes actually get created. So there's a pair of things that happen. You've got your original. At some point you do a fork, and the original continues, but the clone checks the return from fork, sees that it's a 0, and says, hey, I'm a clone, I'm going to turn into something else. It makes a call to exec, and now it's basically some new program. And now you have basically two completely independent programs running, your original and some new program. All right, so we'll play with that tomorrow in some code. I did some of this code in section A's lecture, which will be posted, so you can sneak peek at that. But we'll go through some code tomorrow to look at this, and then we'll build on top of that. So Friday we'll do PA5 demos, and then next week we'll finish up processes, pick up a few other topics, and then do some review. All right, so I'll see you next time.